This is the first in a series of videos about reaction mechanisms. We'll talk about what a mechanism looks like, what an elementary step that makes it up looks like, and then we'll talk about what an intermediate is. So in the last set of videos, we talked about activation energy and how the size of the activation energy determines how fast the kinetics of a reaction might be. And the activation energy comes from a reaction mechanism. So to understand how the activation energy changes, we need to understand what a reaction mechanism is. The activation energy of a reaction depends on the reaction mechanism. So the mechanism is just the path, the series of reaction steps that lead from the reactants to the products. The sequence of elementary steps. Remember when we said that kinetics is a path-dependent field? The path is the mechanism, how we got from the reactants to the products. For example, here is an overall reaction that we might encounter. Two ozone molecules, O3, breaks down into three oxygen molecules, O2. So this is an overall reaction, and from this we know what the reactants are and we know what the products are, but we don't know if this reaction happened all in one step or if there is a series of smaller steps that make it up. So that's why we need to include the mechanism. So the mechanism looks like a list of the steps. So for this particular reaction, the steps are going to look like one ozone molecule breaking down into an oxygen molecule and an oxygen atom. And in step 2, that oxygen atom reacts with the second ozone molecule to make 2 more oxygen molecules. And what we should find is if we add together all of the different steps in a mechanism, we should get a reaction that looks the same as the overall. So we can check this by adding it together. We can add 2 O3s on this side. This oxygen atom cancels out with an oxygen atom on the product side, and then we have 3 O2s that add together to get the same sum equal to that overall. That's an important feature of how a mechanism works. This equation is equal to this equation. So each of these steps is a specific kind of step, and it's called an elementary step. This isn't the same as a normal reaction. We know a little bit more information about these than we do about a normal step. So let's talk about what an elementary step looks like. So you can tell if something is an elementary step by the number of molecules in the reactants. If there's only one molecule in the reactant, it's called unimolecular. And if there's 2 molecules in the reactants, it's called bimolecular. And this is about how many reactant molecules there are. So unimolecular would be 1 reactant molecule that splits up into several others. Bimolecular would mean you had 2 reactant molecules that had to collide with each other, like we learned about in collision theory. And it is possible to have reactant steps with more than 2. If there were 3, for example, we would call it termolecular or tertiary. But this isn't very reasonable. It's not reasonable to have 1 step for a reaction that has more than 2 particles, because all 3 of these particles would have to collide with each other at the exact same time, more than once, often enough for the reaction to happen at the correct orientation and the correct energy. All those features of collision theory would be true, and this is not very likely. So we know for an elementary step to be a plausible reaction that could happen in 1 step, it probably needs to have either one or two molecules colliding. So let's add in our explanation here. So it is unlikely for greater than two molecules to collide Remember the collision theory. And the three facets of collision theory, in order for a reaction to get over the hump, it has to have the high enough frequency, the correct orientation, and enough activation energy. So it needs to have the frequency, orientation, and energy needed. And most of the time, with three molecules, we don't. So we can go back to our first two steps, and we can add labels, uni or bimolecular. So in our first step, we just have one ozone molecule that's breaking down. So this is going to be a unimolecular reaction. And in our second step, we've got a second ozone molecule that collides with a single oxygen atom. That's going to be bimolecular because there's two. And what we can see here from the steps is that the steps don't look anything like the overall reaction. The overall reaction kind of implies that two ozone molecules ran into each other and broke up to produce three oxygen molecules. And what we see from this proposed mechanism is something that looks completely different. These two ozone molecules never actually run into each other. One of them breaks down into smaller components, and the smaller component runs into the other ozone molecule. So there's a lot of information from these steps that we aren't given in the overall reaction. And that's why it's important to look at these. The overall reaction doesn't tell us about the path. But it's important to note each of these reaction mechanisms is experimentally proposed. It is proposed based on experimental data, and it's very difficult to prove a mechanism is true. All right, let's go back to elementary steps. So we know for something to be an elementary step, it has to be unimolecular or bimolecular. And if we can prove that's true, one of the interesting features of an elementary step is the way we can use the stoichiometric coefficients, those numbers that go in front of each of the compounds in the balanced reaction. When we first learned about writing rate laws, we said we would never ever take the stoichiometric coefficient and use it as the order in a rate law because we didn't know for sure if it was true. But in this case, when we have an elementary step, we do know that this is true. The reason we can't do this for a given reaction is because we don't know the mechanism. We can't use this 2 in front of the O3 as the order because we don't know for sure if these two ozone molecules are running into each other. And come to find out, according to the proposed mechanism, they aren't. So for an elementary step, we can do that. We can take that number and turn it straight into the order. So let's practice our newfound skill. So writing the rate laws for the steps is super easy because we don't have to do an entire method of initial rates problem to find the order or plot the concentration versus time in 3 different ways. All we have to do is take the stoichiometric numbers and plug them into the rate law. So for step 1, we'll call this rate 1. We have a K constant, but there's going to be a K constant for every step in the mechanism. So we'll want to call that K1 as well. And it's even better if you go back into the mechanism and you write K1 over the arrow where you're using it. So it'll be rate constant times reactants, which for step 1 is just the O3. And the coefficient in front of O3 is a 1. So the order for this one is a 1. And we can do the same for step 2. Rate 2, it's going to have a rate constant of K2. So we'll throw that over the arrow. And then it has 2 reactants, the oxygen atom and another ozone. And each of those has a 1 in front of them. So the coefficient is going to be a 1. So each of these different orders came straight from the coefficient. So that's a pretty cool trick that we can do. The final interesting part about elementary steps is that we know that one of those elementary steps is going to be slower than the other one. We may not know which one it is. It depends on what the problem tells us. But one of them is going to be the slowest step. And we have a special name for that. We call it the rate limiting, or sometimes the rate determining step. And sometimes it's called RDS for short for rate determining step. And so the rate determining step, I like to think about it with an analogy of me making breakfast in the morning. When I make breakfast, I usually have cereal. That's what that's supposed to be. We'll add a spoon just so we know what that is. And I usually have a glass of juice. And I usually have toast. So if we think about what the rate determining step would be of me making my breakfast, it's the one that's going to be the slowest. And so making the toast is always going to be the slowest part of making my breakfast. And so what that means is that no matter how fast the other steps of the breakfast go, the amount of time it takes for me to make breakfast only depends on how long it takes to make the toast. So even if I was world's fastest orange juice pourer or cereal pourer into the bowl, it doesn't matter how long that takes. It only matters how long the toast takes, because it takes so much longer than everything else. And so what that means is that the rate of the entire process of breakfast basically only depends on how long it takes to make toast. And so that's true for a mechanism, is the rate of the slowest step will determine the rate for the entire process. So let's write that out. That's important. So the rate law for the rate determining step, the slowest one, determines overall rate. Okay, and so these rate laws are going to match. And that's going to be important when we're trying to figure out if a mechanism is plausible or not. So in the next video, we'll talk about when you're given an unfamiliar mechanism, how to figure out if that mechanism is plausible based on what we know about mechanisms and elementary steps.